Want to know how statisticians or data scientists spot outliers with just one glance? Meet the box plot, a powerful visualization that shows you the data spread, the median value, and those weird data points that could be potential outliers. In this video, we are going to explore three essential statistical plots in Tableau, which are histograms, box plots, and scatter plots. These are the go-to visuals that data scientists or analysts use to understand and communicate the story about the data. Whether you are analyzing sales, survey results, or social media data, these plots will help you spot patterns, detect outliers, and uncover relationships pretty fast. We'll also use the histogram as a starting point to introduce you to the concept of probability distributions, explaining intuitively why they matter and how they are used, all through simple and interactive visuals. Alright, let's start by discussing the agenda and get an overview of what we'll be learning in this video. We'll begin by taking a look at the dataset we'll be using throughout this video. It's a fairly straightforward sample dataset that contains height and weight information for 10,000 individuals, males and females. Next, we'll deep dive into the process of building a histogram, first understanding the concept, then implementing it in Tableau. We'll also mathematically interpret the insights histogram offers, explore its limitations, and understand why this naturally leads us to the concept of probability distributions. After that, I'll walk you through an intuitive introduction to probability distributions, focusing on the kind of questions they help us answer at conceptual level, keeping it simple without diving into the underlying mathematics. Next, we'll gain a theoretical understanding of each component of a box plot, and then use Tableau to build the box plot visualization using our height and weight dataset. After that, we'll compare the histogram and the box plot, exploring the unique insights each plot provides, along with the respective advantages and limitations. Lastly, we'll explore how to build a scatter plot, understand its interpretation, differentiate between positive and negative correlations, and finally, interpret a predictive linear model derived from the scatter plot. Great! We have a lot of exciting content to cover in this video. As always, I'll keep things simple with minimal maths and stay focused on our main objective, which is to building effective visualizations in Tableau. So without further ado, let's kick things off by first understanding the dataset. This dataset is quite straightforward. It includes records for 10,000 individuals, evenly split between 5,000 males and 5,000 females, along with their corresponding height in centimeters and weight in kilograms. That's all there is to it. Simple, right? For our first two visualizations, that is histogram and box plot, we'll focus solely on the height variable from this dataset. Let's begin with the histogram first. Imagine you are given a task to visualize the height of all 10,000 individuals in the dataset. As a beginner, you might think about placing each person on this one-dimensional number line according to their height. At first, this seems reasonable, but as you add more individuals, the line quickly becomes overcrowded. The sticky figure representing each person would start to overlap, creating a dense and hard-to-read chart. Even if you replace each individual with a simple green circle or a dot, the problem still persists. The visualization becomes cluttered, making it difficult to derive any meaningful patterns. It means we won't be able to effectively visualize this data using just a one-dimensional number line, right? Now, if we consult a statistician, they would likely suggest an alternative approach. Instead of plotting every individual on a single continuous scale, we divide the scale into smaller segments or buckets and count how many individuals fall within each bucket. These segments are technically known as bins. The size of each bin can be chosen based on our analytical needs. For instance, if we choose a bin size of 5 centimeters, our first bin may cover the range from 135 centimeters to 140 centimeters. And according to the convention of closed and open intervals, a person whose height is greater than or equals to 135 centimeters but less than 140 centimeters would fall into this bin. Similarly, the second bin would span from 140 centimeters to 145 centimeters. Following the same inclusion rule, Individuals with a height greater than or equals to 140 centimeters but less than 145 centimeters would be placed in this bin. This process continues, effectively dividing the continuous height scale into multiple bins, each 5 cm wide. This allows us to assign each individual to their appropriate bin based on their height. As you can see visually, as we begin placing individuals in these bins one by one, a natural pattern emerges. More people tend to fall into the central bins. These central bins are typically around the average or mean height of 10,000 individuals, which here looks like around 165 to 170 centimeters. In contrast, the number of people decreases towards the lower and upper extremes of the scale. This overall trend reflects the height distribution of the population. If we count the number of individuals in each bin and represent those counts using a bar plot, the resultant plot is known as a histogram. In this plot, the height of each bar corresponds to the frequency of individuals within that bin. In other words, the y-axis represents the number of people in each bin. Great! That wraps up the theoretical understanding of histogram. Now let's move on to the practical part. Quickly implementing this plot in Tableau using the height and weight dataset. Just start a new session in Tableau Public and select Microsoft Excel as your data source. Locate the height and weight data file on your hard drive. Here it's stored on my desktop folder, so select it and click open. Since the Excel file contains only one sheet, its data will load automatically. You can do a quick verification to ensure the data looks correct, then proceed directly to the visualization canvas by clicking on the sheet 1. If you observe carefully, building a histogram requires two key components: bins field onto the x-axis and frequency or count on the y-axis. So our first step in Tableau is to define this custom bin size and create a corresponding bins field that we can drag onto the column shelf for the x-axis representation. To create custom bins, right-click on the height variable in the measure section, then hover over create and choose bins. In the dialog box that appears, enter a bin size of 5 centimeters. If you wish, you can rename the generated bin field, but for now, we'll keep the default name. Finally, click OK to create the bins. You'll now see a new categorical field named height bin appearing in the dimension section. So go ahead and drag this field onto the column shelf. And you will observe that all the bins are now neatly laid out across the canvas, each representing 5 cm height intervals. Now, as discussed in the lecture slides, we need to represent the count or frequency on the y-axis. To do this in Tableau, we can drag the generated field called number of records, often displayed as Excel sheet name, weight height, and in bracket counts, onto the row shelf. This will count the number of entries in each height bin, giving us the histogram, right? Alternatively, we can remove this, and if we drag the actual height field onto the row shelf, we will need to change the aggregation of this height variable. Click on the drop down on the height pill and hover over the measure and switch the aggregation from sum to count to achieve the same histogram output. The height of each bar now represents how many individuals fall into each height bin. Make sense? Make sure you're comfortable using both methods, either by placing the number of records directly onto the row shelf or by dragging the height field and changing its aggregation to count. Both approaches yield the same histogram, and knowing both gives you a flexibility depending on your workflow. Cool? Now let's add the frequency label to each bar by dragging the height field onto the label card in the marks pane. Then just like before, change the aggregation from sum to count so that each bar displays the correct number of individuals in that bin. Finally, let's fine-tune the appearance a bit, starting by adjusting this size slider to make the bars slightly wider and change the bar color to green from the color option in the marks pane. These small tweaks will make your histogram more visually appealing. At this point, you should be comfortable making the remaining formatting changes by yourself, such as renaming the chart title, editing the y-axis label, or customizing axis numbers as per your style. So that's how you create a histogram in Tableau. Alright, now that we've understood what is a histogram, how to create it, walk through its construction process, and its Tableau's implementation, let's move to the next part of our session, which is exploring the statistical applications of histogram and gaining an intuitive understanding of probability distributions. While we'll deep dive into the mathematical foundations of these concepts in my dedicated data science, probability and statistics course, but here I wanted to give a conceptual overview, just enough to help you appreciate why these ideas matter and how they tie back to visualizations we are building. So with that in mind, let's explore some insightful applications of the histogram we just created. For simplicity, instead of 10,000 people, let's take a sample of 1,000 people only to make calculation simpler, and the same bin size of 5 centimeters. As a part of your statistics classroom project, you may have collected the height of these 1,000 individuals and built a basic histogram plot as shown here. In statistics, a small data sample from whole population, for example 1,000 individuals in our example, are used to make inferences or generalized conclusions about the entire population. For example, on the basis of this collected data, the key question your professor might pose is, what is the probability that a randomly selected individual from the whole population falls within the height range of 160 centimeters to 170 centimeters? And this is the standard mathematical notation used to represent the probability we are trying to determine. To begin solving this question, we first need to identify the specific height range mentioned here, which is from 160 centimeters to 170 centimeters, corresponds to these two highlighted purple bins. According to the basic principle of probability, we calculate probability as a ratio of favorable outcomes to the total outcomes. In this case, the favorable outcomes are the number of individuals within these two bins, which is 168 plus 176. And the total number of outcomes is the overall sample size, which is 1,000 individuals. So the ratio comes out to be 344 by 1000, which gives us a probability of 0.344 or 34.4%. This means if we randomly choose a person from the population, there's a 34.4% chance that their height will fall between 160 centimeters to 170 centimeters. This is a straightforward example of how histogram can be used in basic statistical analysis, specifically to estimate probabilities from observed data distributions. It is a powerful yet simple application every beginner should understand. I encourage you to observe one more important detail in this example, the range for which we calculated the probability, which is 160 centimeters to 170 centimeters, that happens to be perfectly aligned with the predefined bin boundaries. Now let's make things a bit more interesting. What happens if the range we are interested in doesn't line up neatly with the bin interval we have created? Exactly, that's what we are about to explore next. Let's examine what happens when we are given a general height range that doesn't align perfectly with the bin boundaries. Consider a few example questions. What is the probability of randomly selecting a person whose height is less than 154.5 centimeters? Or someone whose height lies between 156.3 centimeters to 178.7 centimeters? Or someone who is taller than 174 centimeters? In all these cases, these specified values fall within bins rather than at their edges. This highlights a key limitation of histograms. They are not ideal for calculating precise numerical probabilities for these type of arbitrary value ranges. Now before we transition to the concept of probability distributions, let's address another significant limitation of histograms. Just a moment ago, I mentioned that we usually collect a smaller sample from the entire population, like the 1,000 individuals in our example, and rely on it to make inferences or draw broader conclusions about the entire population. So what if in a sample of 1,000 individuals, no one falls within the 180 to 185 centimeter height range? This could very much happen when we are collecting a sample of only 1,000 individuals. Does that imply the probability of randomly finding someone with a height in that interval is 0? Of course not. We know that in the overall population, people within that height range certainly exist. It's just that, due to randomness of sampling, a particular sample may not have captured anyone from that specific range. Now that we have understood the two key limitations of histogram, let's consider how to address them. Wouldn't it be ideal if instead of using these discrete bars, we could represent the shape of the histogram with a smooth continuous curve? Such a curve could seamlessly estimate probabilities for any range, even those not aligned with bin boundaries, and also better reflect population characteristics when the sample data is sparse or missing in certain intervals. Take a small pause and think about it, right? In statistics, we use a specific type of these smooth curves to approximate the overall shape of a histogram. These curves are known as probability distributions, and they help us model how data is expected to behave across a population. There are several standard types of probability distributions in statistics, each suited to different kinds of data and analysis. While we won't dive into the details of these distributions in this course, since it's beyond our current scope, I've included this chart purely for your reference and motivation. It gives you a glimpse into the broader world of statistical modeling that we'll explore later. So stay tuned with me. However, since the shape of our histogram closely resembles to one of the most well-known and widely used probability distribution, the normal distribution, which is also called the Gaussian distribution or bell curve, we can clearly observe how smoothly this curve fits over the histogram, capturing its overall shape and trend effectively. Isn't it cool, right? Now before me tell you a few characteristics of this bell curve, let's quickly calculate the average height of these 10,000 individuals from our dataset in Tableau. First, open a new worksheet by clicking on this new sheet icon, then drag the height field from the measure section onto the canvas. By default, Tableau aggregate this field as a sum. To change it, click on this green pill in the marks pane and switch the aggregation from sum to average. You'll now see that the overall average height of a person is 168.6 centimeters. Also, let's rename our sheets for better clarity. The first sheet as height histogram and the second one as height average. And keep in mind that the average height of a person is 168.6 centimeters. For now, here's a couple of key properties of the bell curve or the normal distribution you should be familiar with. First, the curve is perfectly symmetrical about its central vertical axis. Second, the central axis passes through the mean or average of the data, which is around 168 centimeters height in our case. To help you visualize this, imagine placing a wedge below the curve right at the mean. Because of its symmetry, the curve would balance perfectly without tipping to either side. Cool? This type of curve is known as normal distribution because in nature, many phenomena tend to follow this pattern. For instance, as we have seen with height variable, if you were to plot a histogram of weight from the same dataset, you would notice a similar bell-shaped distribution. Other real-world examples of variables that often follow a normal distribution includes your SAT scores, blood pressure measurements, IQ scores, and many more variables. As a fun and simple activity, I suggest you to explore more such variables on Google and observe their distribution shapes. It's a great way to build your statistical intuition and recognize patterns in everyday data. Awesome! It's now time to develop a mathematical intuition for the importance of probability distributions and understand how they address the limitations of the histogram when it comes to estimating probabilities or chances. I'll briefly introduce a few fundamental mathematical concepts, nothing too deep, so stay with me for a few minutes and follow along attentively. First, let's recall a simple concept from your high school maths class, the equation of parabola. For example, consider an inverted parabola with the equation of 4 minus x square, which is a quadratic function. Just like the parabola has a mathematical equation, probability distributions also follow specific mathematical functions. This means that this normal distribution curve, for instance, is not just a smooth line. It has a well-defined mathematical equation behind it. For your reference, I've included the normal distribution function here. Don't worry if it is your first time seeing it. The takeaway is simple. Every probability distribution is essentially just a mathematical function. That's all you need to remember for now. Another important concept to recall from your high school maths is the area under the curve. Do you remember how we used to calculate the area beneath a curve? For example, if I want to calculate the shaded area under this parabola between x equals to 1.1 to x equals to 2, what mathematical concept should we apply? If you are thinking of definite integrals, then you are absolutely right. Kudos to you. So the shaded area represents the area under the curve, and to calculate its exact numerical value, we simply integrate the parabola's function over the interval from x equals to 1.1 to x equals to 2. That's all there is to it. The actual result of the calculation isn't important here. What matters is that you understand the process to find the area under a curve between 2 points. To find the area under the curve between the 2 points, you apply definite integration to the function over that interval. Simple. Now let's extend the same concept to find the area under the probability distribution. For example, if you wanted to compute the area under this normal distribution curve from 155 to 180 centimeters, you would have to integrate this complex function from x equals to 155 to x equals to 180. Even a person with masters in mathematics would shy away from calculating this manually by hand. Fortunately, we have computers that can perform these complicated calculations in a fraction of a second. And that's exactly why we'll use Python programming to compute such calculations with just a single line of code. I hope now you have a clear understanding of what probability distributions are in this context and the logic behind computing the area under any mathematical function. Making sense, right? And since probability is fundamentally a fraction representing part of a whole, the total probability can never exceed 1. That's why the total area under any standard probability distribution curve is always equals to 1. Cool? Let's now conclude this introduction to probability distributions by revisiting the earlier questions that could not be answered effectively by histograms. The first type of questions that histograms struggled to answer was determining the probability of randomly selecting a person with a height less than 154 centimeters. Remember, this value 154 centimeters lie within a bin rather than its bin boundary, right? But now that you have understood the concept of probability distributions and their underlying mathematical functions, we can say that the probability we are trying to calculate is simply the shaded area under the normal distribution curve. And we learn to compute this precisely using just a single line of Python code in the upcoming data science, probability and statistics course. For now, having a clear conceptual understanding is all that matters. Another type of question that this estimated normal distribution answers with ease is the chances of randomly selecting a person having a height between 156.3 centimeters to 178.7 centimeters. Again, the answer is this shaded area under the distribution that can easily be computed using Python. And finally, the last type of questions we can easily answer involves calculating the probability of randomly selecting a person whose height exceeds a specific value. In this case, it's 174 centimeters. And we can again use Python to calculate this specific area under the curve accurately and efficiently. That brings us to the end of our introduction to probability distributions. While we won't be creating probability distribution plots in Tableau just yet, it's certainly possible once you grasp the underlying mathematical concepts like mean and standard deviation. Since histogram naturally lead us into the concept of distribution, skipping this topic would have left a gap in our understanding. My goal here was to provide you with a conceptual foundation, a simple intuitive explanation of what probability distributions are, why they matter, and how they help us go beyond the limitations of histogram. I hope this gave you some clarity and sparked your curiosity. We'll explore these distributions more deeply and mathematically later in probability and statistics module. But for now, this overview should be more than enough to build your intuition. Now let's begin by understanding the background of box plots and then proceed to create a few of them in Tableau. Remember how we created the histogram earlier? We only use the height field for that. First we place all individual heights on the x-axis and then we group them into height bins for cleaner visualization. This binning process allowed us to neatly organize the data and display it as a histogram. Awesome! So far, you have clearly grasped the concept of histogram. Now rather than placing these bars on the number line to create a histogram, statisticians come up with a smart technique. They mark the numbers or summary statistics directly on this number line itself. And this clever arrangement forms what we call a box plot. Let me now show you exactly what that looks like. To get started with understanding box plot and to simplify the maths, let's again imagine a sample of 1000 people only. And we put them along a number line based on their heights, just like we did earlier with the histogram. To truly grasp what a box plot represents, I urge you to stay focused for the next 5 minutes as we work through a few key questions that lay the foundation for understanding this visualization. So the first question we are asking is, what should be the height of the person such that they are taller than approximately 25% of the population but shorter than around 75% of the population. This numerical value below which 25% of the population lies is denoted by the symbol Q1, which in this case is a height of 161 centimeters. This means a person with a height of 161 centimeters is approximately taller than 250 individuals in the population. This Q1 is also known as first quartile or lower quartile or 25th percentile. Does it make sense? Here I would like you to pay attention to two important terms, quartile and percentile. I'll provide you a summary of these terms at the end of this slide. Similarly, the next question we aim to answer is, what is the height of the person who is taller than roughly 50% of the population and is shorter than the remaining 50% of the population? The numerical value below which 50% of the population falls is represented by Q2, which is in this case correspond to a height of 168 centimeters. This implies that a person with a height of 168 centimeters is approximately taller than 500 individuals out of total population of 1000. This Q2 is also referred as second quartile or 50th percentile, and in statistics, this special value is also known as median of the data. Lastly, we want to answer what is the height of the person who is taller than approximately 75% of the population but shorter than remaining 25%. The numerical value below which 75% of the population falls is denoted by Q3, which is in this case is a height of 176 centimeters. This means that the person with a height of 176 centimeters is taller than approximately 750 individuals out of total population of 1000. This Q3 is also known as third quartile or upper quartile or the 75th percentile value of the height data. So here we come across two important terms, quartiles and percentiles. To summarize quickly, we can say that these three quartiles divide the data into 4 equal parts, 25% each, or 250 individuals between each quartiles, while percentile divide the data into 100 equal parts, each representing 1%. For example, below first quartile or Q1, we have 250 individuals, and this value is also known as 25th percentile. Making sense, right? And if I talk about a general percentile, such that if your height corresponds to 10th percentile, it means you're taller than 100 individuals but shorter than rest of the 900 individuals. Make sense? Alright. Now let me ask you an interesting question. What percentage of population or how many individuals lie between Q1 and Q3? Take a moment to think carefully before answering. If you guessed that 50% of the population or 500 individuals lie between Q1 and Q3, then you're absolutely right. As I mentioned earlier, each quartile interval represents 25% of the population. So from Q1 to Q2 is 25% and Q2 to Q3 is another 25%, adding up to a total of 50% of the population. So we can conclude that the middle 50% of the population lies between first and third quartile. And the numerical distance between Q1 and Q3 is known as interquartile range or IQR. So in this case, the IQR is calculated as Q3 minus Q1, which equals 176 minus 161, that is 15 centimeters. Therefore, within this 15 centimeter height range, starting from 161 centimeters to 176 centimeters, we find approximately 50% of the population or 500 individuals out of 1000. Simple, right? I hope this concept is absolutely clear to you now. Now, before I throw a brain teaser question your way based on these basic concepts, take a moment to pause and go over all this information thoroughly. Make sure you're fully absorbed and understood every bit of it what is displayed on this single slide. Alright, ready? So here's the question. Let's start with IQR. Grab your notepad and divide the section into two parts, A and B. In section A, take the IQR to be 30 centimeters and in section B, take the IQR to be 5 centimeters. Now think carefully, what visual impact will each of these IQR values have on their corresponding histograms and the box plots? Please take a moment and do this simple activity. Don't skip it. This is a classic interview question often asked to test your conceptual clarity on histograms and box plots. Now let's learn how statisticians use a box plot to identify extreme values or outliers, and how this final step completes the assembly of this box plot. The next element in the box plot is called whiskers. Not the kind of whiskers found on cats and dogs, but the lines extending from each side of the box plot in both the directions. Let's define the whiskers mathematically, starting with the lower whisker first. So the lower whisker starts from Q1 and ends at a certain point left to Q1 on the height axis. This lower point can be numerically found as the value of Q1 minus 1.5 times the value of IQR. So in our case, it is 161 minus 1.5 times 15, which equals 138.5 centimeters. So the lower whiskers ends at a height of 138.5 centimeters on this height axis. Similarly, the upper whiskers begins at Q3 and extend to a specific point to the right of Q3 along the height axis. Similar to the lower whisker, this upper point can be calculated using the formula Q3 plus 1.5 times IQR. So in our case, it is 176 plus 1.5 times 15, which equals 198.5 centimeters. Therefore, the upper whiskers ends at a height of 198.5 centimeters on the height axis. Cool? That's the method we generally use to draw whiskers on a box plot. Statisticians have empirically observed that about 95 to 99% of the data typically falls within the range of lower whiskers to upper whiskers. Hence, it is reasonably safe to assume that any extreme data points lying beyond these whiskers on either side are potential outliers and should be examined more closely. So in this case, the person lying below the lower whisker could be considered as extremely short, and the persons lying above the upper whisker are considered as extremely tall. We might want to isolate these people for further analysis. Awesome. All these components together, such as quartiles, whiskers, median, potential outliers, and this cool visual, forms what we call a box plot. I hope you now have a clear and complete understanding of elements of box plot and how it all fits together. Let's implement the box plot directly in Tableau and see it come to life with a height and weight dataset. To get started with the box plot, let's first open a blank canvas by creating a sheet and rename it to height box plot. To create a box plot visualization, our first step is to place every individual height value onto a single axis and then put a box around it. So remember, it's a two-step process, okay? So here in Tableau, I'll start dragging the height field from the measure section onto the row shelf. This action places height field on y-axis by default. Also displays a single bar representing total sum of height values, which is approximately 1.6 million centimeters for the 10,000 individuals in our dataset. But this isn't what we want. We are not interested in total height. Instead, we want to see individual data points. So in short, we need to deaggregate the height field to split it into values for each of 10,000 individuals. Do you see the challenge here? Cool. As always, once you understand the problem, the solution becomes straightforward. To deaggregate the height measure, go to the Analysis tab in the menu bar and uncheck the second option labeled as Aggregate Measures. Tableau might take a moment to process, but shortly after it will display each individual height data point separately. So as we discussed, our first step, which was placing individual height values on a single axis, is complete. Now all that remains is the second step, adding a box plot around these individual data points. Now to convert this visualization into a box plot, go to Show Me tab and from the chart suggestions, select the box plot located in the second last row. This is how we can easily create a box plot in Tableau. Although we can certainly create a vertical box plot, since we have discussed the element of box plot using the horizontal orientation, let's switch the height axis from vertical to horizontal by clicking on this swap button. This changes the orientation of the box plot from vertical to horizontal. Now all that remains is to format and refine the aesthetics of the box plot to make it presentation ready. Let's quickly format this plot and you can follow along. First, fit the box plot to the entire screen by selecting the entire view from this drop down in the Fit toolbar. This makes the box plot appear more prominent. Another way to enhance the visual appeal is to address this empty space. Now looking at the data, the minimum height of an adult is clearly above 130 centimeters. So why not start this x-axis or height axis from 130 centimeter onwards? Makes sense, right? To do this, right-click on this height axis and select Edit Axis. And in the pop-up, under the Range section, instead of keeping it on automatic, choose Custom. You will notice the axis currently starts at 0 centimeters, which doesn't make sense for adult's height. Enter 130 centimeter as a starting value and close the window. Now the box plot is neatly stretched. The axis starts from 130 centimeters and the plot appears more informative. You can also hover over the box plot to view all key metrics we just discussed. Note that Tableau uses slightly different terminology for these metrics. For example, what we typically call the first quartile or Q1 is labeled as lower hinge in Tableau. The median is referred to as Q2 and the third quartile, Q3, is called the upper hinge. So don't be confused by these straightforward naming differences. Now while you enjoy the music, I'll give this plot a more refined look. Feel free to follow along with my formatting style or apply your own. So that's how we create a box plot and a histogram for the entire height variable. And we can clearly see that the individuals with heights below the lower whisker or above the upper whiskers are considered extreme values. For an adult male or female, height around 138 or 139 centimeters are considered quite short, while a height of 200 centimeters is abnormally tall. To further analyze and drill down into who these individuals are, we can place their actual names onto the detail card in the marks pane. However, since we don't have names in the dataset, but we do have their unique ID number. So let's drag ID onto the detail card instead. Now when you hover over a specific dot representing a person's height, you will also see their unique ID. This also helps us isolate individuals who are either extremely short or unusually tall compared to the rest of the population. So this is how we can easily spot extreme values or potential outliers with just a quick glance at the box plot. Appreciating it, right? Now you have the essential theoretical understanding of both plots covering the maths, logic and Tableau implementation. Now it's time to compare the pros and cons of box plot and histograms and determine which plot to use in different scenarios. We created histogram and this box plot without considering gender. But this time we'll first create two separate height histograms, one for males and one for female, to quickly compare height distribution across gender. Then we'll similarly split the box plot by gender. And finally, we'll compare the histogram and the box plot to understand their respective insights. Cool? So now let's open up a new sheet in Tableau and name it Gender Height Histograms. Just like before, start by dragging the pre-calculated height bin field onto the column shelf and the height field onto the row shelf. And instead of using the sum aggregation for height measure, let's change it to count so that the y-axis displays the actual frequency for each bin. Now if you would like, you can adjust the size of the bars to make them appear closer to each other. And to split the histogram by gender, simply drag the gender onto the row shelf. This will instantly divide the chart into two, female on the top and males at the bottom. Pretty cool, right? Now you can easily distinguish the height distribution by gender and observe that the average height of males is considerably greater than the average height of females. And if you would like to check the actual numerical value for gender-wise average height, you can quickly create a new sheet and name it Height Statistics. In this sheet, drag the gender field onto the row shelf and place the height field onto the canvas where ABC text labels appear. And since we want to view the average, change the aggregation of height pill from sum to average. Here we can clearly see that the average female height is approximately 162 centimeters, while the average male height is around 175 centimeters. If you go back to the histogram distributions, you'll notice that the center of female height distribution, which is following a normal pattern, aligns with this 162 centimeters average, and the male's height distribution centers around 175 centimeters mark. I hope these simple statistical values are making sense to you. Okay, now let's give these plots a quick aesthetic touch. Instead of using this standard view, select entire view from this fit drop-down in the toolbar, and to differentiate between these plots, drag the gender field onto the color card in the marks pane to color the plots by gender. These default colors aren't very pleasing, so I recommend customizing them. To do this, go to this color legend and select Edit Colors, and for females, I'm choosing a soft pink, and for males, a light teal. Once selected, hit OK. For now, I'll leave the remaining formatting choices to you, such as removing these grid lines and unnecessary labels. Alright, now that the gender-wise histogram are taken care of, let's create the gender-wise box plot for the comparison between histogram and box plot insights. Here we created the height histogram from scratch, but for the box plot, let's be smart. Instead of starting from scratch again, let's duplicate the existing box plot sheet by right-clicking on the sheet name and selecting the duplicate option. Double-click on the name of the duplicated sheet and rename it to Gender Height Box Plot. And let me drag the sheet to position it right next to the gender height histogram. Now just like histogram, our goal is to split this plot by gender. So go ahead and drag the gender field onto the row shelf. And as soon as you drop it, the box plot will split into two. One on the top is for females and one below for males. And finally, let's drag the gender field onto the color card in the marks pane to maintain consistent aesthetics across visualization. And here too, we can observe that median height for females is noticeably lower than for the median height for males. Just like we previously calculated the average height for males and females in this height statistics sheet, let's now also compute the median height for both genders as well. First, let me widen this table a bit and then drag the height field again onto the text box on the canvas. This creates a new column that currently shows the sum of all heights. So right click on this pill and change its aggregation from sum to median. The second column in this table now displays the median heights for both males and females. And just to recall, what is the median height? It's the height of a person who is taller than roughly 50% of the population and shorter than the remaining 50%. And here, the median height for female is 161.88 centimeters, while for males, it is 175.33 centimeters. And if you're wondering why median height is so close to the average height, it is due to the beauty of the normal distribution. Since the height field in a dataset closely follows the normal distribution, one of its key properties comes into the play. So for a normal distribution, mean and median values are almost identical. We'll discuss these properties in more detail in another course. For now, let's return to the box plot. So from this visual, we can clearly see that the median female height is lower than the median male height. Cool? So now that we have created both gender-wise histogram and box plot, it's finally time to compare histogram versus box plot. Observe these two plots carefully and take a moment to think which plot provides more statistical information, histograms or box plot. Yes, the box plot definitely outshines the histogram when it comes to providing numerical information about the data. So we can conclude that the box plot are excellent for summarizing and comparing datasets as they highlight median, quartiles and outliers. But histograms too have their own charm and aura. Can you think of a few scenarios where histogram might be more useful than a box plot? That's exactly what we'll explore in the next slide. For our next comparison between histogram and the box plot, I'm introducing a new dataset that contains just one field. The dataset represents grocery delivery times for the past 20,000 orders from a delivery startup that claims that their average delivery time is around 70 minutes. Now, just like we placed individual heights on x-axis when we discussed histogram and box plot, let's place all the delivery time values on the x-axis here as well. Just by looking at these time values on the x-axis, do you notice something unusual? Most of the delivery times are clustered in this zone, making this zone a bit denser, while relatively fewer delivery time data points fall in this other zone, making it comparatively less dense. This makes sense too. From the business standpoint, if everything runs smoothly, most deliveries would cluster around the claimed average time of 70 minutes. However, if there are occasional supply chain or logistic issues, which we can reasonably assume aren't very frequent, some deliveries might take significantly longer, even over 4 hours. Relatable, right? Now, to gain clarity on the statistics like median and quartiles, we can transform these delivery times into a box plot. Here we can observe that the median delivery time is around 54 minutes, meaning approximately 50% of the total orders, around 10,000 orders, were delivered under 54 minutes, while the remaining 50% or the remaining 10,000 orders took longer than 54 minutes. This all looks good and makes sense, but analysts often need to answer more sophisticated and statistical questions from this data. Questions that can help business optimize its performance metrics. So the mathematical concept that enables us to answer such question is understanding the underlying probability distribution. So just as the height variable approximately followed a normal distribution, we may want to determine which probability distribution best approximate this delivery time data, right? And do you think is this box plot capable of showing the distribution shape? No chance. In short, box plot cannot reveal the distribution shape of the data. But here's the good news. We have already learned about histograms. So when we transform this data into a histogram plot, the hidden shape of data distribution will reveal itself. Therefore, we can conclude that histograms are excellent for showing the distribution shape and bin frequencies, which help statisticians determine the kind of probability distribution the data might follow. Now, looking at the shape of this distribution, one thing is clear. It's definitely not a normal probability distribution, just like we discussed in the case of height variable. The exact name of this distribution we'll explore in the advanced distribution sections of the statistics course. But coming back to our discussion, now you should be able to understand the advantages of histogram over the box plot and vice versa. I won't be showing you the Tableau implementation of these plots using this delivery time dataset because this part has been deliberately left for you. You will find the dataset in the resources dataset folder along with few questions related to it in this section's assignment. There you will need to create both of these box plot and histogram visualization in Tableau and answer a few interesting business questions based on these insights. So good luck for that. That wraps up our discussion on histogram, distributions and box plot. Now let's move on to the next important plot type, the scatter plot, along with key statistical concepts like correlations. Up to this point, we have been working with a single variable, such as height field, by placing the individual values along a single axis. This one numerical variable alone was sufficient to create both histogram and box plots. Through these visualizations, we have explored their significance in depth and uncovered various interesting statistical insights each plot could reveal. Now what if we want to visualize two numerical variables at the same time, say height and weight? The goal here would be to uncover any hidden relationship or pattern between a person's height and their weight. To begin building this visualization, we need to keep in mind, since we are working with two numerical fields here, we'll require two axes, one for each variable, in order to create the plot effectively. And the statistical question we are aiming to answer, is there a quantifiable correlation between the individual's height and weight? To put it simply, this correlation helps us determine whether an increase in a person's height has any effect on their weight. So to begin creating this visualization, we can start by placing the height field on the x-axis and weight field on the y-axis. On this two-dimensional Cartesian plane, each individual is represented as a single dot, where the coordinates correspond to their height and weight. For example, a person with ID equals 2, his height is around 174 centimeters and weight is around 73.5 kilograms. Similarly, we can continue placing each individual on this plot one by one. Once all individuals are represented as a dot in this two-dimensional space, the resulting visualization is known as a scatter plot. Therefore, simply by plotting pairs of numerical values like height and weight on a two-dimensional graph, we get a scatter plot. Easy, right? Let's quickly implement this scatter plot in Tableau to explore any hidden relationship between weight and height in our dataset. To begin with the scatter plot, let's first create a blank worksheet and rename it to height weight scatter plot. We can start by dragging the height field from the measure section to the column shelf to set it as the x-axis, and drag the weight field to the row shelf to place it on the y-axis. Now let's break down what just happened here. Instead of displaying each individual as a separate points on this two-dimensional height versus weight graph, Tableau by default aggregated the data. It is showing the sum of all heights and sum of all weights as a single data point on this plot. This behavior is similar to what we observed earlier while creating the box plot. There Tableau automatically aggregated the height field and showed the sum, right? And just like we handled it earlier, we'll deaggregate the measure by going to the Analysis tab in the menu bar and unchecking the Aggregate Measure option. Now you can see each individual is represented by a separate circle, accurately reflecting their unique height and weight on the scatter plot. Additionally, if you drag the ID field onto the detail card in the marks pane and hover over any of the circles on the scatter plot, you will be able to notice the person's unique ID along with their corresponding height and weight values. This is how we can effortlessly create a scatter plot in Tableau. Now let's move on to the formatting the plot for better clarity and presentation, and then we'll explore the statistical insight this visualization has to offer. Cool, that should do the job perfectly. As always, I'll leave the final touches of formatting to you. To uncover the insights this scatter plot is pointing towards, it's essential to understand the concepts of correlation. Let's understand correlation intuitively without delving into mathematical details of it. Correlation helps us understand how a change in one variable influences or is associated with a change in another variable. For instance, in this scatter plot, we observe a general trend. That is, as height increases, weight tends to increase as well. And when a relationship like this is visible, we describe it as a positive correlation between height and weight. Conversely, if height increases but weight decreases, we would say there is a negative correlation between height and weight. And if there is a case where height increases but there is a little to no change in a weight trend, we can conclude that there is no correlation or negligible correlation between height and weight. This is how we can intuitively understand correlation with the help of these visuals. Now, looking at the scatter plot we just created, what do you think about the relationship between height and weight variables in our dataset? That's right, we can clearly see that height and weight are positively correlated over here. Awesome, now that you have an intuitive understanding of what correlation is, let me make it a step further and discuss the extreme cases of positive and negative correlations. If you observe that the point form a perfectly straight upward sloping line, meaning that every increase in height is consistently matched by an increase in weight, then we say there is a perfect positive correlation. And the correlation coefficient is +1. But if you observe that the point form a perfect straight downward sloping line, meaning that every increase in height is consistently matched by a decrease in weight, then we say there is a perfect negative correlation, and the correlation coefficient comes out to be -1. Thus, from a mathematical standpoint, the value of correlation always ranges between -1, indicating a perfect negative correlation, and +1, indicating a perfect positive correlation. Although we'll explore mathematical definition and correlation formula in the statistics course, but since I've given you an intuitive understanding of correlation, for now, let's just compute the correlation for our scatter plot in Tableau and see how much height and weight are correlated with each other. Since correlation is represented by a single numerical value, we can use Tableau's built-in function to compute the correlation coefficient. For that, I need to create a calculated field. Just right-click on this empty space below the measure section and choose Create Calculated Field. Name the calculated field as correlation, and inside the formula editor, to calculate the correlation, we will use the cor function. Simply input both fields, height and weight, separated by a comma within the function. Then click OK. This creates this calculated field called correlation, and to display the correlation value, create a new sheet and rename it to correlation tile. And finally, drag the correlation field onto the canvas. You'll notice the correlation between height and weight is quite strong, approximately 92%. That's good. Just like we previously added sales and profit tiles in our first dashboard, we can simply include this correlation value tile onto the dashboard next to the scatter plot. Cool. Now that we have observed a strong correlation between variables, such as in the case of height and weight, it might be tempting to conclude that an increase in height causes an increase in weight, or to infer a causal relationship. While in this case, it might be reasonable to believe that an increase in height leads to increase in weight, in general, we must be cautious of it. High correlation value does not always imply causation. It's a common analytical trap to assume one variable causes the other without further investigation. Let me show exactly what I mean by it. A classic coincidental example is the observed positive correlation between the ice cream sales and the drowning incidents in the US. From the historical data we have seen, as the ice cream sales increases, so do the number of drownings. And analysts have computed a reasonable positive correlation between these two variables. While this may sound alarming at first, it doesn't mean ice cream sales causes drowning. Instead, a lurking variable, summer season, explains both. People eat more ice cream and also swim more during hot weather, which increases the risk of drowning. Another widely cited humorous example of misleading correlation is the inverse relationship between the number of pirates and the global average temperature. As the global pirate population has declined over the years, global temperature have risen. suggesting a negative correlation. However, this is purely coincidental, and there is no causal link between the number of pirates and the climate change. Therefore, it is important to be cautious, as these examples clearly demonstrate that correlation does not necessarily imply causation. So without sufficient data and domain knowledge, we should never infer a causal relationship between two variables solely based on their numerical correlation value. Now moving on to the final section of this video, let's explore how even a simple scatter plot like this can provide a glimpse into the world of statistical modeling, prediction, and machine learning. Sounds cool, right? I'll just give you an intuitive teaser for now, without diving into the mathematical details, as these concepts are reserved for upcoming machine learning course. Don't worry if you come across a few unfamiliar terms, just remember that concepts like these exist. You can always revisit this section later once you have gained a deeper understanding during the machine learning course. Ready? This is the scatter plot we created earlier. Now to build a linear model, we need to estimate this linear trend mathematically. We are trying to find out the equation of this best fit line that represents the relationship between height and weight. So we use this historical data, and an optimization algorithm calculates the relationship between height and weight for us. As a result, it provides the equation of best fit line in terms of height and weight variables. That is, weight equals 1.38 times height minus 159.23. Let's set aside few metrics like r squared and p-value for now, and concentrate solely on the derived equation of the line. The optimization algorithm that determines this best fit line is commonly known as linear regression, and the resulting mathematical relationship or this function is simply referred to as model in the language of machine learning or data science. I hope you are getting a good high-level understanding of these concepts. Take a moment to let it all sink in. Once you are ready, I'll walk you through how to implement this linear model directly within Tableau. Now this linear trend can be easily represented using Tableau's trend line feature. To insert the trend line or the best fit line, first navigate to the analytics pane. Here, click on the trend line and then drag it onto the scatterplot area. And from the list of options that appears, drop it onto the linear box. We'll explore the other types of trend lines in the upcoming section, but for now, let's stay focused on the linear model. As soon as you drop the trend line onto the scatterplot, Tableau instantly displays the linear model line. By hovering over this line, you can view the equation, which represents the generalized mathematical relationship that defines how height influences weight in a dataset. This is the very relationship we aim to uncover. And that's how easy it is to insert a linear model trend line onto the scatterplot in Tableau. Now comes the most exciting part. You might have been wondering, why do we even need to estimate this linear equation or mathematical relationship in the first place? Well, that's exactly what I'll explain in the final slide of this video. TLDR, we created this linear model in order to predict the weight of any new person by inputting their height into the model. Imagine someone tells you that their height is approximately 175 centimeters, and you want to estimate their weight for whatever reasons. But there is no weighing machine around. Fortunately, you remember the model's equation from this course that relates height to weight. So you simply plug this person's height into the model's equation. And with a quick calculation, you get an estimated weight of approximately 82 kgs. Of course, there will be a margin of error, perhaps a few kilograms. But you still get a reasonable estimate of the person's weight. This is the basic idea behind making predictions using linear models. And it's just not limited to this example. This is the core approach across data science and AI world. We build mathematical models from historical data, and when new data comes in, we input the values into the model to generate predictions. Certainly, building such models in the real world demands a solid foundation in mathematics and coding. However, for the scope of our Tableau course, this level of mathematical introduction is sufficient to spark a curiosity and interest in further exploring the fascinating world of data science, machine learning, and AI. With this, let's end this statistical discussion over here. As always, I'll be publishing this workbook onto the Tableau public, and you will find both the Tableau workbook and these lecture slides available in the course resources.